handful of flour here, and then some tomato stuff, and oh, solo mio. Oh boy, this cooking stuff, there's nothing at all to it. I love to cook. Oh, let's see again.
Something smells real good in
Hi,
here.
Mr. Z.
Hey, Watson.
Yeah.
The little green gourmet, huh?
Yep.
Look at this. You've got a chef's hat.
Uh-huh.
Now, I'm ready for my lesson.
All right.
Now, today we're going to turn the tables on Give Science a Hand. Thanks for tuning in. Watson is going to be the teacher, and Mr. Z here, I'm the student. Now, Watson promised to teach me how to make a pizza.
Yep.
Watson, I didn't know you were Italian.
Well, gee.
Yeah, you have everything you need here. Let's see. Olive oil.
Olive oil.
And we've got flour
Right.
and tomatoes and rolling pins. Looks like we're all set.
Yep,
okay,
sure are.
Teach. What's
Okay.
the first part of my lesson?
Well, first thing we're going to do is take a couple handfuls of the flour over here and put it in this bowl. And
Wait a minute.
What?
The students out there are going to be listening to you, Watson, because they're going to try to make the pizza. Now, if you say take a couple handfuls of flour, what's a handful?
Well,
I mean,
gee.
my hand's bigger than yours, and their hands are different sizes.
Tell you what, Mr. Z, let's use your hand. Your hand's bigger.
Use my hand. See how he tries to worm his way out of things? So we use my hand because we'll get a bigger pizza.
That's right. Yeah.
All right, let's see how much. We've got to be a little more specific here. Now, how much of this olive oil do we need?
Oh, we're going to splash a couple drops in.
A splash of olive oil. I mean, just a couple drops. Just
sure.
A little
just
bit.
a few. Just enough.
And I guess you just want a couple tomatoes, right? Doesn't matter how
I
many.
love tomatoes. Let's put all the ones we have in there. Yeah.
Watson, this is a science show. We're going to have to be a little more specific for our audience out there.
Oh, yeah?
Yeah. Now, of course, every good student, every good cook knows that you need measuring tools. Now, here are some measuring cups, but I guess Watson decided they were here for decoration. Is that right, Watson?
Well, I was going to use it a little later.
Sure he was. Now, if you're paying attention, in your science lab or in your kitchen, you need some basic equipment because on the side of this olive oil, it says 118 milliliters.
Oh, gee, what's a milliliter,
What's
mister?
a milliliter? That's a very good question. Milli is a prefix that means 1/1000th, and liter is a unit we use for measuring volume, liquid volume. So if you have a graduated cylinder, we've used this on our program before.
Oh, yeah, I've seen that before.
Yes, or if you have a beaker, you can measure out the amount of olive oil you need. Now, our recipe says here, and Watson was going to tell you this, our recipe requires 50 milliliters of olive oil.
Oh, gee.
So to do that, what are we going to use, Watson?
Well, we're going to use a cylinder with milliliter scale.
All right, so we would pour our olive oil up to the 50 milliliter mark, so now everybody understands exactly how much is required.
Oh, it makes it the same every time then,
yes, couple drops or a splash.
Yeah, well, gee, what do I know?
And of course the flour, Watson said use a handful.
Right.
This bag of flour, it says, contains 907 grams. Watson, what do we use to measure grams with?
Oh, gee. I guess we could probably use the scale.
We could use the scale. Watson's knowledge of grams extends as far as graham crackers, I think.
Yep, you got that right.
We need a triple beam balance here, and we can measure grams on this scale. Now, our recipe requires 100 grams of flour, so we know exactly how much to measure.
Oh.
Are you getting the hang of this, Watson?
I think so.
Yeah, specificity of measurement. That's the key to a successful recipe or a successful science experiment. Last thing. We talked about liters and volume. We talked about grams and weight. And one other unit we need to remind the students about is we need a ruler for it.
Oh,
what do you think?
That's a meter.
That's a meter. These are actually centimeters along here. We measure distance. If you want to measure how high the dough rises, all right, you might have to do that in millimeters or centimeters, and that's why you need a ruler.
Oh, Mr. Z.
Yes, what?
I got an easy way to remember that.
An easy way to remember all these things, liters and meters and grams?
Yeah, I'll make up a point.
What do you want to say?
A meter goes the distance. A liter fills her up. A gram is worried about its weight. This metric stuff ain't tough.
That even rhymes.
Yeah, I know.
Watson just waxed eloquent for us with his little poem there. That's not bad, Watson.
Thank you.
Meters and liters and grams, if you know those, if you know the different prefixes that tell you what fraction of each one you need, then you're home free as far as cooking and experiments go.
Yep.
Now, what's this?
That was a little something I had while I was cooking.
I've never had a pizza made with Coca-Cola before. Were you going to do that, Watson, or were you just drinking from this?
That was for me.
Yeah. Were you going to share it with me?
Well, it's sort of all gone now.
Yeah, thanks a lot. Now, it says on the side here, on the side of this soda can, it says 354 milliliters. Now, we could have used...
how do I know there's really 354 milliliters in there, Mr.
So
Z?
you don't trust the Coca-Cola company, huh?
Nope.
Well, Watson is good to be a little skeptical. There really are 354 milliliters in here because there is a bureau of the government that makes sure that all of the measurements across the country are exactly the same.
Oh, really?
Yes, and that is called the National Institute for Standards and Technology.
Oh.
And it's right nearby in Gaithersburg, Maryland.
It is.
In fact, Watson.
Yeah.
I have a set here of weights. What do you see this? It looks like buried treasure because they're all gold.
Ooh, look at that.
Can you see that?
Yeah.
This is a standard kilogram. Now, kilo means 1,000. This is 1,000 grams.
Uh-huh.
All right, and as we go down the row, we can see this is a 500-gram weight.
Yeah.
And we keep going down until we get to the tiniest of them all. This is a single.
Look at that. Yeah.
What do you think that is?
That's 1 gram.
That's 1 gram.
Yeah.
Now, we can use our triple beam balance, the one we have here, and use these standard weights and measures, but out in Gaithersburg, they have the standard gram. They make sure that grams and liters and meters all are the same throughout the country. In fact, Watson, this is going to appeal to you.
Okay.
I know you're into pizza, but I also know you have a sweet tooth.
Yep, sure
Now,
do.
if you look over there, do you see that Snickers bar?
Yep.
All right, now out there you can see they have digital scales which are a lot more accurate than this triple beam balance.
Gee,
and
what?
Look, can you see the tiny little weights they have there, just like the ones we showed you here?
Yeah, except they're smaller, some of them.
Some of them are very small, but you can see that they have to be extremely specific so that when you go out and buy a candy bar and it says on the side it weighs a certain number of grams, you can be assured that that's how many are inside.
Oh, gee.
Yeah.
Is that what they do at that place all the time, Mr. Z?
That's what they do there all the time, Watson. But there's something else they're concerned about.
Uh-huh.
Do you see this cookware we have?
Yep.
All right, you have a rolling pin here.
Uh-huh.
Is this to keep away the pizza stealers, or do you need this to roll your dough?
Oh, I use it for dough.
Now, this pan or this pot that we have here made of glass has to be able to withstand a certain amount of heat. Now, the standard for this glassware, as well as the standard for most everything else in your kitchen, is set at the National Institute for Standards and Technology. In fact, Watson, I took a field trip there recently, and I looked at some of the materials that we see in our everyday lives, and we tested them to see how well they could resist fire. Something we should be concerned about.
I'd like to see that.
All right, let's go have a look and see something that could actually save your life. Stay with us. Watson, it is really hot in this room. We're still at the National Bureau of Standards, and the reason why I want to put on these safety goggles is because of this machine right in back of me. And I would rather be hot now than in a place where there was an actual fire and my life was in danger. This is serious business. And the next time you're on an airplane, those of you that are watching, those of you that are sitting in your living room right now or in your classroom, the materials all around you, the wood, the plastic, and some of the things that are in your carpet, like I have here, are flammable. Now, how flammable are they? How soon would they ignite if there was a smoldering fire in that room? And once it caught on fire, how fast would that fire spread? Those are key things to know because your life could be in danger. To show us how that works, we have a machine here called a flame spreader machine. It evaluates how fast a flame can spread and how fast something ignites. We're going to use materials like these. This is a piece of carpeting, like you probably have underfoot right now. If you look up from where you are, most likely you'll see something like this. This is a ceiling tile. How fast would this catch on fire? And how fast would that flame spread? If you're in an airplane and you're looking around and you're not looking at the stewardess and you're not looking at the magazine, you'll see something like this. This is in the ceiling and on the side panels. This has to be tested. You wouldn't want to be in a plane where the material was too flammable. And what we're really going to use today is this. You recognize it? This is from your screen door. This is a piece of plastic. It has a fancy name, PMMA, and I'm not going to try to attempt to pronounce what it really is, but it's a sophisticated polymer. And if it's in your screen door, it might be the barrier between you and safety, depending on how fast it breaks into flame. So we're going to test that now on this machine and show you exactly what they do here at the Bureau of Standards. To help us out, Scott Dolan's going to come on over. Scott's got more equipment than I do. He's better protected. He's got gloves on, he has on a smock, and he's also got on some safety goggles, some glasses. Scott, why don't you load it up? Okay. All right, in goes the panel. And if you'll notice there's some aluminum foil attached to that piece of plastic. That's so that the material reaches an equilibrium, so that the energy is equally distributed throughout that, so when it's ready to burn, it burns all at the same time. Okay, we see a pilot light down there. and there's radiant energy coming from this heating panel on the left-hand side. So if you watch closely, keep an eye on that, Watson. We see that it's starting to decompose, and for this particular material, we know it takes about 2 minutes for the ignition point to be reached. Let's see how fast that flame takes flame and spreads along the material. Don't worry, Watson, I'm not in any danger here. This is a controlled fire, but you can see the flames are getting closer and closer to me. If you look carefully, you'll notice that nothing remains behind. That flame goes all the way through that plastic panel that's in there, so there's no margin of safety. That's why it's very important that we put the right materials in the right places, like in our homes and our schools where our lives are at stake. Stay with us. Now, you've got to promise, all of you, not to tell Watson about this. Now, if he knew that I came and I was meeting one of the astronauts from the Space Shuttle Discovery, he'd never talk to me and never work with me again. Now, on this program so far, we've been talking about weights and measures. We've been to the National Institute for Standards and Technology. We've been looking at grams and centimeters and milliliters and been talking about heat-resistant materials. Well, this is a special treat for Give Science a Hand. Mr. Mike Lounge is here. He just came back from the flight of the Space Shuttle Discovery, America's triumphal return to space, and he's here to talk to us about weights and measures and heat-resistant materials. Mike, thanks for coming on the program.
Sure, Dave. It's good to be here.
Now, one of the reasons Watson isn't here is because we all know he's got a sweet tooth, and we didn't want him to eat the props. We've got some space ice cream here, some astronaut strawberries, and something that doesn't sound real good, beef and rice with onions. Mike, I've got to ask you, have you ever eaten this astronaut ice cream?
No, I've never seen it. I've heard a lot about astronaut ice cream, and I get a lot of questions. What's it like? Unfortunately, the space shuttle, at least so far, doesn't have a refrigerator.
Oh, it doesn't?
We got cold, chilled water, but no refrigerator, except if an experiment that we carry on board for science purposes has a refrigerator with its package, and that occasionally happens. But for food, we don't enjoy that luxury.
So all of the food you take into space has to be consumed quickly if it's fresh, or it's got to be treated in some way. So
we don't really have much fresh food. We have bananas and apples that we can eat early in the mission. Most of it is like this. It's packaged a little differently, but the content is about the same. And that could be quite good, really. Add water to that, heat it up, and it's like a camping trip.
Beef and rice with onions. You're not getting too many potential astronauts out there, Mike, I think, by encouraging, showing this kind of food. Now, on the bottom it says there 29 7/10 grams. Now, in outer space, how much would this weigh?
Well, weight is a funny thing. Weight really means how hard does an object press down on the table it's sitting on, for instance. And if you're, we call it weightlessness, because things don't weigh anything when we're in orbit around the Earth. We're falling, constantly falling.
So gravity is still pulling on you, even though you're in outer space?
That's what keeps you in orbit.
If there was no gravity, you would just continue off and you'd not come back.
Go to places unknown. But we obviously stay close to the Earth. We skim around the surface about 200 miles high, but we're falling all the time. So you don't weigh anything. For instance, if this table was in the space shuttle, it would be falling also. So there would be no pressure between the package and the table. The mass of this would still be reflected by 29.7 grams, but not the weight.
So that's a good point. Mass stays constant even if you get to a weightless environment, but the weight does change. Now, we've also been talking in this program about heat-resistant materials. Now, we know that the space shuttle has to re-enter the Earth's atmosphere, which is a critical time. And oftentimes we see pictures of the underbelly of the space shuttle glowing bright red. Why does that happen, Mike, and why is it you're able to return and not be incinerated?
Well, the space shuttle belly gets pretty hot, over 2,000 degrees Fahrenheit. And the reason it gets hot is to re-enter the Earth's atmosphere and land, you have to slow down. In orbit, we're going 5 miles a second, 17,000 miles an hour. We land at a speed of about 200 miles an hour. So we have to get rid of that energy somehow. And the way you get rid of that energy, the way you put on the brakes, is you skim along the top of the atmosphere and let the atmospheric drag slow you down. That produces heat. That heat is absorbed in tiles like this one in your display here. The entire underside of the space shuttle is coated with some 30,000 of these silicon tiles. It's really like a glass fiber that these are made of. And and they're quite capable of withstanding that 2,000 degree
We have a
heat.
propane torch here. Mike, if we would turn this on and put it against this tile, and if I would put my hand behind it, would I be able to feel any of that heat?
No, I wouldn't hesitate to hold that tile. You wouldn't notice it.
And what kind of temperature can it withstand? What's it designed to withstand?
Well, the hottest parts of the underbelly get to about 22 or 2,300 degrees. That's right behind the nose and maybe the leading edge of the wing. The rest sees anywhere from 1,500 to 2,000 degrees, the black tile.
And then when you're talking degrees, you're talking centigrade or Fahrenheit?
Well, up there it doesn't matter much, but those are Fahrenheit numbers.
Okay.
Yeah.
All right, we want to thank Mike for coming on the program today. We hope some of you potential astronauts out there are encouraged by his presence, and now you know a little bit more about some of the food in space and some of the heat-resistant properties aboard that shuttle. Mike, are you going to promise not to let Watson in on this secret?
I won't tell him.
Okay, I think let's see, you've got a picture here and a patch. You'll never know where this came from. Stay tuned. We're back. Watson.
Yeah.
Now, did you learn your lesson well?
Yeah, I learned that you can trust labels, and you should always measure things so that they come out the same each time. And gee, but
he's getting there.
Yeah.
He's getting there. Okay, Chef. Now that you know the importance of liters and meters and grams and pieces of measuring equipment, and you know that everything in the kitchen is safe because of the standards that are set out there in Gaithersburg, let's get back to our lesson. I'm getting hungry, and this stuff just isn't going to make it. What's next in make?
Hey, which one of you guys ordered the pizza here?
Mister, we're in the middle of a television program here.
Mr. Z?
I didn't order a pizza.
Well,
Watson?
I wanted to make sure we had all bases covered, and
you ordered the pizza?
Yep.
And you told me you were an expert pizza maker.
Well, this is going to be an expertly made pizza.
I'm sorry, buddy. I mean, it's not your fault. I didn't mean to take it out on you. How much is this? How much?
$8.
$8. Okay. Where's this from? Three Brothers.
Yep.
Yeah.
Okay, here's 10. Why don't you keep the change?
All right, take
Thanks
care.
a lot.
Thanks a lot.
Yeah, thank you. Gee, Mr. Z, thank you.
Ordered a pizza.
Yeah, thanks for buying it for me.
With pepperoni on. This looks awfully good.
Yeah, I know.
You're never going to see it.
What?
Listen, you set me up here. You said you were going to teach me and the students how to make a pizza. Then you go and order one.
Well, there's a pizza.
Know what you made? You made the telephone
That's
call.
right.
All right, let's see. Let's make Watson earn his pizza. Does this smell good? Watson, can you see that pizza?
Ooh, look at that. Look at
it looks so good.
Yep.
As I say, you're not going to taste one morsel unless you can answer a couple questions for us.
Okay.
All right? See if you can do as well. I don't know if Watson will share the pizza with you. We can trust to his generosity. Here's your first question, Watson. Are you ready?
Yep.
All right. This can of soda, as we said, has 354 milliliters.
Right.
Question. How many cans of this would you have to drink a full liter? Keep in mind that a milliliter is 1/1000th of a liter. And this can has 354 of those milliliters.
354.
Okay, Watson.
600. Oh, 3, Mr. Z, 3.
You're going to drink 3 cans because 3 times 354 is going to take us just over 1,000 milliliters, which is the same as 1 liter. Was that a lucky guess, or did you figure it out, Watson?
No, I added it all up.
So smart.
Yeah.
All right, here's your second question. If an Olympic athlete runs 100 meters, what fraction of a kilometer has he or she run?
See, a kilometer.
Now, we told Watson before that kilo was a prefix that meant 1,000.
1,000, yeah.
So if the athlete runs 100 meters, what fraction is he going to run?
Oh, 1/10.
1/10.
Yeah.
100 over 1,000, and if you reduce it to lowest terms, we get 1/10. Boy, you're cooking here, Watson. You really want that pizza, don't you?
Yeah.
He's earned 2 slices so far. There are 5 big ones in there. Here's your third question.
Okay.
Aspirin is normally packaged in tablets that are measured in milligrams. Question for Watson and for you, how many milligrams in 1 gram?
Milli. 1,000?
1,000. We already said.
Got that right too, yay!
We said that a milliliter was 1/1000th of a liter, so a milligram must be 1/1000th of a gram.
Oh, gee.
You're doing very well, Watson.
Okay.
And then we went to the Bureau out in Gaithersburg where they measure the standards, and we talked about things in the kitchen that resist fire. Do we call pieces of equipment like this fire resistant, fire retardant, or fire protectant?
Oh, that's fire resistant.
Yes, I gave that one away.
Yep,
all right,
thank
you got
you.
4 slices of pizza. Here's your last question.
Okay.
If this pizza weighs 500 grams, how much of it will be left after I give it to you? How's he going to answer this one? How much?
Well, there'll still be 500 grams, but they'll be in me.
They'll be in you.
Yeah.
Oh, the glutton here we have is the chef.
Yep.
You know who you remind me of, Watson?
Who?
Garfield the cat.
Oh.
Did he take lessons from you in eating?
Yep. Where's that pizza?
Yes, don't take any lessons from Watson in cooking, but I do hope you learned some lessons today about measurement and about standards and about how not to order a pizza if you promise someone you're going to make it for them. Right, Watson?
Yep.
All right, a promise is a promise.
Yep.
You get your pizza.
Yep. Oh, thank you. Hey.
You come back and see us next time. Watson's going to be a little heavier, I think, if you eat this whole thing.
Yep.
Thanks for coming to give science a hand today. Bye-bye.
Hey, Garfield, move over. Mr. Z, I can't believe I ate the whole thing, and my tummy's normally 20 inches. What do you got here? 56! Oh, that's centimeters, Mr. Z.